Before we go on, I want to do a little recap of this amazing scientific crash course that you all have just gone on over the last few weeks. So we started out this section with a lab where we calculated from what scientists call first principles, which is basically just math, the temperature that the Earth should be just based on how much energy reaches Earth from the sun. And we found that it should be this frozen block of ice in space. And we talked about how the reason that we are not a frozen block of ice in space is because of the greenhouse effect. The fact that gases like H2O, carbon dioxide, and methane act as this blanket that keeps the Earth warm by catching long-wave radiation and radiating it back down to the Earth's surface. And without it, we would be much, much colder. And then we talked about how the uneven distribution of sunlight coming into the Earth causes the equator to be warmer than the poles. The fact that the equator is warmer than the poles sets up these global scale air circulation patterns that basically serve to take warm air from the equator and bring them up to the poles or down to the poles. We know that that process causes the oxygen isotope ratio of the oceans to change, right? So we take light oxygen, oxygen 16, out of the ocean, bring it to the poles, and turn it into ice. And using this process, we were able to see the long-term change in Earth climate as recorded by benthic foram shells that are sampling ocean water, and it's sensitive to that change in temperature and ice volume. Okay, so from this climate proxy, we saw that Earth went from a very warm period to now, a relatively cold period over the last 50 or so million years. And that before that, there was even, a warmer period about 90 million years ago where the Earth was so warm that, there was like tropical plants and cold-blooded animals at the poles. There was no ice anywhere. And we have since gone into this much colder period as shown by those forams. All right, and we learned that the process that took us from that warm period to this cold period is probably chemical weathering, which was the dissolution, right, dissolving silicate rocks by acid rain, by CO2 and rainwater that are dissolving rocks and taking carbon dioxide out of the atmosphere and storing it in the rock record. And it's the weathering of the Tibetan Plateau that started being uplifted about 50 million years ago that has caused this long-term cooling over the last 50 million years. On shorter timescales, like the last 800,000 years, we've seen that the variations in Earth's orbit around the sun based on these three parameters, eccentricity, obliquity, and precession, have caused the volume of ice on Earth to vary sort of cyclically, right? So here's, again, the oxygen isotope record of the oceans, and we see that the volume of ice on Earth has oscillated or gone back and forth from periods where there's a lot of ice, which are these low points, to periods where there's relatively less ice, which are these higher points, and that this process is driven by these changes in Earth's orbit, which control the amount of solar radiation that hits the North and South poles. We also learned that there is a climate feedback that participates in this process, whereby when things get cold enough for ice sheets to grow, more and more ice will then grow because it's cold. That increases the Earth's albedo and ends up reflecting more light out back to space, right? So this positive feedback kicks off, making things get cooler and cooler and cooler until the orbital parameters change, and then there's more solar insolation, and the same process works in reverse, where things get warmer, so snow melts, that decreases the albedo, and then causes things to get even warmer and warmer. And then finally we saw that the ice itself, that the ice sheets in Antarctica and in Greenland and all over the world provide a record of the atmospheric concentration of the greenhouse gas CO2 over the last 800,000 years. And we know that this is not a climate proxy, it is a direct measurement of ancient air bubbles that are trapped in the ice, and that they tell us that the concentration of CO2 in the atmosphere has varied over the same 800,000 years, and it sure looks like the concentration of CO2 varies in a very similar way to the volume of ice on Earth, and that we think that this is controlled by changes in the orbital parameters of Earth around the sun. Finally, we saw that during glacial periods when the Earth gets cold, that one of the reasons it's able to get colder is because CO2 is stored in the deep ocean, so there's less of this greenhouse gas in the atmosphere, causing the Earth to be colder and for there to be more ice. Before we go on, I want to just talk a little bit about this process and how it works together with those orbital cycles and what that means for the global concentration of CO2 in the atmosphere and why we should care about it. I want to use this diagram to think about how the concentration of CO2 in Earth's atmosphere and the temperature of Earth might vary through time in response to these different processes. Okay, so time is going to go from in the past on this side towards the present over on this side. And on our vertical axis here, we're going to have both temperature and CO2 concentration. And I'll show the CO2 concentration in red and also with a dashed line to kind of make it clear. Okay, so first let's consider a situation where the Earth is relatively warm. Okay, so we're going to be at point 1 here. The Earth is relatively warm. Okay, so here's temperature. Black, solid black line. So if the Earth is relatively warm, and then the orbital cycles of the Earth line up to decrease summer insolation and kick off the ice albedo feedback. I'm going to call this feedback A, which causes Earth to cool off. If we think about the ice albedo feedback, we remember that this feedback can work in 2 directions. So we're going to think about example A, where the climate is cooling. That causes more ice and snow to form. That increases the albedo of Earth's surface, makes less solar radiation absorbed by the surface, which further cools the planet. And that's a positive feedback that makes things cooler. Okay, so that means that here at time 2, the temperature is going to start to decrease because of the ice albedo feedback. However, that decrease in temperature doesn't have anything to do with the concentration of CO2 in the atmosphere. So that might continue sort of relatively unchanged until at time 3, right, the fact that the Earth is cooling off changes wind patterns around Antarctica. It shifts the circum-Antarctic winds to the north and makes upwelling less efficient, causing CO2 to be retained in the oceans. So that might cause a decrease in the amount of CO2 in Earth's atmosphere. But it's sort of going to happen after the initial cooling caused by the ice albedo feedback. Okay, so temperature is going to decrease, and CO2 is going to decrease, which is also going to help make it colder. Right, and eventually we're going to sort of hit time 4 here, where the Earth is in a relatively cold and icy setting, right? So temperature has gone down. This is sort of an ice age, right? We can think of this as the last glacial maximum. All right, sometime later on, the orbital cycles of the Earth around the sun are going to line up to increase the solar radiation that's hitting the poles and kick off the ice albedo feedback that works in the opposite way, ice albedo B, which if we come back to this diagram, it's the same feedback, just works in reverse, where now we've got a warming climate, which means that there's less snow and ice, And that decreases the amount of light that's being reflected away from the Earth and means that more solar radiation is absorbed, which warms the planet. Okay, so now this feedback is going to serve to warm things up. Okay, so the orbital cycles start to warm up the planet, and that warming is going to cause the global wind patterns to go back to how they were before, right? So it's going to push the circumantarctic winds back down to the south, strengthen upwelling, and release CO2 that has been stored in the deep ocean back into the atmosphere. But it's the warming that's caused by these orbital cycles that allows that to happen. So similarly, that means that the concentration of CO2 is going to increase in response to the warming that changes the ocean circulation. And that would be sort of time 6 over here. And then eventually we'll sort of go back into a warm period, and this whole process will start to repeat, as we've seen that it does over the last 800,000 years. So this is an important concept, that the orbital parameters are kicking off these other processes that serve to cool the planet and draw down CO2. And it introduces this concept of a lag time. So there's this amount of time in between where depending on what climate proxy you're looking at, the temperature of the Earth might be decreasing, colder, like before the concentration of CO2 is actually being drawn down. This is called a lag time. And importantly, depending on which kinds of climate proxies you're using, and even where on Earth these climate records come from, this can change the lag time of our climate records. It can get longer, it can get shorter. In fact, there are even some situations where the CO2 will go down before the temperature does. So it's a very complex relationship, and it is different for multiple different kinds of climate proxies. So I'm sort of just describing the ones that we've talked about in detail, but there are many more and many other feedbacks that are all sort of playing into this this process. But so this idea of how this feedback has caused climate to vary over the last 800,000 years, it begs the question of whether or not CO2 is really responsible for the change in temperature, or is CO2 changing just in response to other forcings? Or another way of saying that is CO2 just along for the ride? Or does CO2 have the power to change the temperature of Earth's surface on its own? Before we begin a discussion of modern greenhouse gas emissions, we should take one more look at this plot and see how CO2 has varied over the last 800,000 years. Between 180 and 280 parts per million, that's been the concentration of CO2 in Earth's atmosphere for just shy of the last million years. If you recall from earlier in the semester when we talked about the composition of Earth's atmosphere and defined a few greenhouse gases, we said that the current concentration of CO2 in the atmosphere was 0.04%, which is the same as 400 parts per million. So on this axis, 100 parts per million above 280 would be 380, and we're just above that at 400 parts per million. Of course, time is going in this direction, so what we should really do is bring this curve way up like that. Okay. So the current concentration of CO2 in the atmosphere is much higher than it has been for the last 800,000 years. So it's worth asking, how did the current CO2 concentration in the atmosphere get so high? How has it become so elevated? To answer this question, we've got to think back to our different carbon reservoirs. So remember, we've got the atmosphere, the biosphere, the shallow and deep oceans, and the geosphere. The atmosphere, we estimate, has about 600 gigatons of carbon in it. Remember, a gigaton is a billion tons, so that's 600 billion tons. The biosphere has just a little bit more, 610 gigatons. Much more carbon in the upper ocean, a lot more in the deep ocean, and a whole ton in the, 66 million billion tons in the geosphere. Okay, so remember that the atmosphere and the biosphere, they exchange carbon very rapidly by plants photosynthesizing and animals respiring, sort of cycling on a scale of years to decades. And the same thing with the atmosphere and the upper ocean. The atmosphere and the upper ocean are exchanging carbon. Same thing, years to decades. And we just saw how over the last 800,000 years, the deep ocean has been exchanging carbon dioxide with the atmosphere, on those glacial, interglacial cycles, and that happens on a scale of sort of thousands of years. And the geosphere, right, the Earth's largest reservoir of carbon, if we remember, the geosphere doesn't really exchange carbon dioxide or carbon in general with the atmosphere or the biosphere or the ocean very quickly. It does this over millions of years, right? Millions of years it takes to exchange carbon between any of these reservoirs and the geosphere, right? Because once carbon gets locked up in rocks, it takes a long time, has slow geologic processes have to happen before it can exchange with any of those other reservoirs. So exchange with the atmosphere in particular takes place over millions of years. However, the current concentration of CO2 in the atmosphere has been greatly elevated over what it's been for the last 800,000 for over 1 million years. And the way that happened is that human beings figured out a way to take carbon out of the geosphere, use it to make energy, and use that energy to power stuff. So of course, we should all be familiar with the little schematic pump jack I've drawn here, right? This is Texas. We've all seen pump jacks around. So, human activity taking hydrocarbons out of the ground, things like the coal we burn for electricity, the natural gas we use to heat our homes, or the gasoline we use to power our cars. We can burn that carbon that is locked up in rocks, and we can turn that into energy and do stuff with it. But the consequence of turning that carbon into energy is that it puts CO2 back into the atmosphere. And instead of this happening, this transition of carbon from the geosphere into the atmosphere happening over millions of years, human activity is making this happen on a much, much shorter time scale. So, when we see this plot and understand the processes that cause CO2 to vary over the last 800,000 years, and we understand that they're caused by orbital changes in the Earth's path around the sun and changes in the storage of CO2 in the oceans, right? We say, well, the concentration of CO2 in the atmosphere doesn't determine temperature. It's controlled by orbital forcings and ocean circulation. That was true for the last 800,000 years, but now a whole lot of new CO2 has been added to the system, right? There's way more CO2 in the atmosphere than there has been for a very long time. And so this is a disturbance to a system. So here we see a system that's going back and forth very regularly. Picture a pendulum on a clock or something, right? It's just going back and forth, back and forth. And it's happy to do that, for a long time. However, now there's been some disturbance, right? We've increased the amount of CO2. And so, we've smacked the pendulum on the clock, right? It's out of time now. There's been a disturbance to this natural system. So even though we understand that the natural changes, that the concentration of CO2 is sort of following other processes, now that there's been a lot more added, many people are concerned that this will cause significant problems for the Earth's environment, right? For the biosphere, for the oceans, right? Like big problems for life on Earth. So why do we think that this rapid change in the concentration of CO2 might cause big problems for life on Earth? Well, I'm a geologist, and so I always think of, to look into the past to try to see, is there a previous example where something like this has happened in Earth history before, and can we see what happened, and maybe try to make a decision of whether or not we think this current issue is a real problem based on what's happened in the past. To find an example of when in the past, when in Earth's history, there might have been a similar experiment run where lots and lots of carbon that was stored up in rocks was suddenly put into the atmosphere. We're going to have to go back all the way, almost into geologic time, way back to week 1 of this class in your very first lab. So this map might look familiar. This is the global map of rock types at the surface of the Earth. And the reason I'm showing you this map now is to highlight this purple blob in Siberia. I'm just going to outline it here. This big purple blob kind of goes around like that. This giant purple blob is a thing called the Siberian Traps. The Siberian Traps are what's called a large igneous province. It's basically a giant volcanic field. I mean, this thing's like the size of Australia. It's gargantuan. The Siberian Traps are a large igneous province of almost entirely basalt that was erupted 251 million years ago. How much basalt? About 1 million cubic miles of basalt was erupted from 251 million years ago to 250 million years ago. 1 million cubic miles of basalt erupted. It's huge. So what's the significance of 1 million cubic miles of basalt erupting 251 million years ago? When the Siberian Traps erupted, 1 million cubic kilometers of basalt was extruded onto the surface of the Earth. Now, we may recall from the section where we talked about the different properties of different kinds of volcanoes that basalt is a mafic igneous rock, and mafic volcanoes tend to be lower in their gas content than felsic volcanoes. But when you erupt 1 million cubic kilometers of it, there's still a lot of gas that's coming out of the Earth. So Some of this gas, a lot of it would have included CO2, of course, is a greenhouse gas, right? So we've got CO2 being emitted to the atmosphere directly from volcanoes. But in an extremely unfortunate coincidence, the Siberian traps erupted through these layers of sediment and injected all their magma sort of into these layers of sediment that were sitting around in Siberia 251 million years ago. It just so happened that these sediments happened to be very, very, very rich in hydrocarbons. So imagine if a magma system started to move through the oil fields of Texas. Well, all this magma is really hot. It ignited all of the hydrocarbon reserves in these Permian sedimentary rocks. So that means that even more CO2 was emitted from that was burned off of these sediments. All in all, it's estimated that between 30,000 and 100,000 gigatons of CO2 were released during this large igneous event, during the eruption of the Siberian traps. Between 30,000 and 100,000 gigatons. So that's 30,000 billion. That's a lot of CO2. So this is a very similar experiment in Earth history where lots of carbon that was stored up in rocks, either in the deep mantle or as organic carbon in these sediments, was suddenly released from the geosphere into the atmosphere. This was 30,000 to 100,000 gigatons of carbon dioxide over 1 million years. Between 251 and 250 million years ago. Okay, so what else happened at this time? What else in the rock record might leave some evidence of this experiment that the Earth conducted 251 million years ago when it suddenly took lots of carbon from the geosphere and added it to the atmosphere? So last week, you all had a lab looking at the rate of change in temperature, going into and coming out of all the last glacial periods as recorded by the ice cores. So to wrap things up, rather than calculate a change in temperature rate, what we're going to calculate is the rate at which CO2 was added to the atmosphere during the eruption of the Siberian traps compared to the rate at which CO2 has been added to the atmosphere in the last 200 years due to human activity.